Welcome everybody to this final session. It's amazing you made it. My name is Elahe and I'm head of AI research at Wayve. And I'm trying with this last session first and recap everything that was discussed today very briefly, and then discuss also very briefly at the end the advancement, challenges, and the future direction for the end-to-end autonomous driving systems. The agenda would be first, we will go through why end-to-end compared to modular systems, and then what was the advanced and technology up to here. We will go through the simulators, world modeling, language for self-driving, and at the end, we will discuss the directions and the challenges for the future research. Some of those will include like data scale, safety, memory efficiency, and so on. The first question is the why end-to-end autonomous driving. This diagram was shown a few times already today. I go very briefly into that. The traditional autonomous driving, which also we know them as a modular approach or AV 1.0, they are combined of multiple modules. They have perception, planning, prediction, localization, and many more modules that they are all working stack back to back with the hand engineering systems to make the autonomous driving work. These systems already, they are very complex. Each are coming with more, like each component comes with its own error that end up to have a cumulative error or compound error effect at the end of this decision-making process, which leading to be a non-scalable solution, and it's constrained with the hand engineering rules, and their reliance heavily on the HD maps make them also reduces their applications, because many roads are changing over the times. Every single day, the roads, even in the urban area in the cities, are changing, and then new rules are new roads are added, and then you are driving out of roads, not everywhere, that very frequently the maps are getting updated based on that. In AV 1.0, as I mentioned already, the individuals modules are coming with the errors from individuals modules are compounded over the time, creating significant system errors. And also the safety of these systems at unknown situations still it is question. Although later we will come back to these concepts that maybe it's in the community, it's more accepted that they are more interpretable because you know what should be the output of each module, but how the modules all together end up to interact with the world is still unknown, and the safety scenarios are limited there. In contracts, we have end-to-end AI systems or AV 2.0 that we are combining all these modules into one neural networks. And then we let the system to decide and optimize for these errors that every individual modules in the AV 1.0 has to work with. This approach eliminates the need for intermediate representations and allowing for direct optimization for the end results, as I already mentioned, and it's more scalable. Something that we haven't touched it yet, these both systems, they need safety subsystems because of regulations and also the public trust that later at the end of the session, we will go through that. Why end-to-end systems? These systems are highly portable because they use uniform computation structure. They can easily adapt to new kind of hardware settings and also vehicles, and simplifies development with fewer modules, which is a huge advantage, and achieves better performance compared to these traditional human-coded systems or rule-based design systems. This makes them a compelling choice for future autonomous driving solutions, and that's why the whole tutorial was around the end-to-end systems. One very important thing we need to remember is that perception is crucial for our decision making, but in the real world and real challenge, it lies in the decision making process itself. Embodied AI must generalize to new unseen situations and adapt to different vehicle types and geographies. This is what it's coming at the decision-making process. Although the system can realize the traffic signs and many other maybe objects, but still the decision-making, how to interact with this dynamic world and evolving world around it, that's the major challenge. This challenge itself requires robust decision-making capabilities that go beyond a simple environment perception. This coming from a very nice survey paper that today was briefly discussed. I want to touch it back because we can, after establishing, okay, we have AV 1.0 and 2.0, and 2.0 comes with many more advantages over the first modular systems approaches, the conventional approaches. Now how we can test and verify and train these systems. We can use real world data, we can test them or even use the closed loop data, and we can do this verification and validation over open loop. There are so many challenges. Some of them we already mentioned, it was already touched. One thing that I want to specify here is that interpretability is different than explainability. And still it's a question that do we need to that the systems to be interpretable, or we want them to be just explainable. Interpretability maybe goes more at the like the level or modules, more than just the whole process, if the system make any decision and can explain the root cause of that decision. And some of the future trends that it's like zero shot or few shot learning. Why we need that? Because every day we might come with a very new scene and scenario that nothing similar to that was already included in the data base that the models were trained. And these few shot learnings are very useful. Imagine you are driving in Europe and then you go to USA, or in UK and then USA, or the other way around. You can quickly adapt yourself from right-hand side driving to the left-hand side driving. And these capabilities are coming with the few-shot learning or zero-shot learning, or even the traffic signs from one country to the other country slightly might change. And if you just train your models to be to learn based on this memorization or recognition of the traffic signs perception modules that is coming with AV 1.0, then this might be very limiting our driving system to just one country. Let's now recap some of the recent advances and technology in the field that was already discussed, and this includes generative models for trajectory prediction, data-centric approaches for continuous improvement, and the integration of language models into the driving systems. The generative models, they are coming with many advantages. This includes text and video models trained on supervised video and at the internet scale text data. Very huge amount of knowledge. It's already there available. And this is coming to us how to use them and leverage this knowledge from the text into our decision-making process. These models show emergent reasoning capabilities and enhanced planning in the combination with the word models and the video generations. High fidelity simulators are crucial. Why they are crucial for different aspects. It's coming from the training, generating the edge cases, which is very hard and scarce to capture in the real world, or sometimes they are very dangerous and we cannot even try to capture those data. We should avoid as much as possible. And in other cases, because they are so rare, then there is almost impossible to drive, or you need to drive millions of kilometers to capture these scenarios. And then the simulation comes handy to generate for the training purposes, also for evaluation. And it goes from open loop that has the model output doesn't interact with the simulator and doesn't impact the states of the simulator, to the closed loop, which the model interacts with the simulator and the state is changing over the time based on the action. A word model was, Gianluca did a great job, went through the many papers. I'm going back to a basic definition of it. A word model is generative models that predict future states based on the current state and the action. And these models are valuable for dynamic and reactive simulations, something that at Wayve we are using at the moment. And also they are very useful for what if, creating this counterfactual experimentation, something that they are very useful again for the safety scenarios, for checking if the action and language are already grounded, and many other use cases are coming with the counterfactuals. And then the model-based reinforcement learning and search-based planning. These models are key to advancing autonomous driving technology, and their use cases is going beyond that. This was already also shown, but for re-emphasis on how the field is growing so fast from within a year almost, how many papers are coming in this field, and still there are so much room for improvement. And I hope this tutorial is just encouraging you to pick some of the topics, some of the challenges and unresolved problems, and then start working on them. The other concept that it was just before this session was discussed is the multimodality integration into the driving system. One of these very useful modalities is the language, because it comes with a huge knowledge which we can use the internet scale data for acquiring that knowledge. And now we have vision, language, action models that they are interacting, and they can use for different purposes, for making the system more safer, more trustable, because they can explain their actions, and also to making more informed decision making, and also coming with zero-shot inference. Explainability was one of the reasons behind the language models. There are other opportunities also coming with the language in autonomous driving. One of them is the intelligence, this huge knowledge that comes. And the other one is the trust and safety. If the model can reason behind its action, not just taking an action based on some perception and planning, but can reason like what's going on around me in the environment, and how every other agent around me is going to interact with me and react even maybe to my action, then this reasoning, if it's there, then the public can trust such a model more than the others. This is a great summary of the differentiation between the AV 1.0 and AV 2.0. The AV 1.0 is rule-based. It's coming with many modules for perception, prediction, planning, and also the reliance on HT maps. They are not robust to OOD, and also they are not scalable. And because of HT maps, their application is very limited to the route, to the routes that already we have the HT maps for. The the AV2 2.0 has also data-driven approach and principle-based approach. The difference is that for principled approach, we have multimodality, and then we use word models and so on. This approach comes with the knowledge from the whole internet. It's a real world, and also the reasoning behind interaction with the real world physics and the prediction. It enables zero-shot generalization, and we can make use of chain of thought reasoning. And Wayve, it's already pioneered in using the principle-based approaches. Many of our papers and the blog posts is coming, such as Lingo 2, that is already in the same era. Now looking ahead, we already have many challenges that we have had some advancement in those, although none of them are fully solved. But there are coming with a few more challenges. This includes diverse real-world scenario, managing vast data scales that will come or we need, ensuring safety, making quick decisions, and optimizing efficiency. Unique challenges that we are in the real-world deployment for autonomous driving facing at this time, they include processing massive data. This massive data could be handling diverse and unpredictable, like we don't know how much more data we need to capture to handle those. And at the same time, every single day and every deployment that we have on the road, it brings more data, and how we are going to train, how we are going to manage, and how we are going to update the models based on this new data, that's also another aspect. Therefore, there are two different directions with handling a huge data set. Data scales, also the safety concerns that I will discuss briefly, optimization and the decision making. These roads and the interacting with all dynamic agents in the road, even the static objects like the traffic signs. They are static traffic lights, but they are changing in a fraction of time. And then the system needs also to interact in a fraction of second or even less than that to be in a safe condition. We need a lot of data. Why? Because every single day we might come with a novel combinations, such as this one, that it acts like a mirror that is showing, instead of looking like a truck or another vehicle, it could act as a mirror. Or a rare object on the road. It could be any animal or any unknown even object. And then people are in that area creative. They can wear a stop sign or any other traffic signs, or they can dress up like a cone. And then this might be very confusing for the systems that only based on the perception, and planning is only coming from the perception-based knowledge, not a more reasoning and decision-making process that it's beyond that. there is a very big challenge with AV 2.0 is that the explainability. It's such a black box. But in general, all deep neural networks are a black box. There are millions of parameters, and then explainability of these systems are really hard. Planning and predictions also the networks that we are training right now, they are scaled poorly with respect to the input-output temporal length. The systems, they don't have a memory. How we can
We
add
have
memory
a technical issue again.
Okay.
So we can't hear you now.
Okay.
But it is resumed. Okay.
Okay, great. Yeah, one of the other things is that with the input-output temporal lengths, the networks, they don't scale or scale very poorly. We need a memory, how to add memory to the systems. This is not only for end-to-end system, it's for even the modular systems. We have this problem. How to add common sense reasoning because of all these unpredictable scenarios that we might face, and how to add change of rules or add edge case without retraining everything from scratch. This slide also was shown today, and this is very useful because when we are dealing with edge cases, we need way more data to collect than to capture any of those rare cases. But can we, with the generative models, bridge this gap with what we need for the training and what we can capture in the real world scenarios? This is another area of the research that could come very handy. But at the moment, still all this simulation-based training, at least, they are suffering from the sim to real gap that is there. Memory was already mentioned. We as a human, it's coming from Daniel Kahneman, this hypothesis that brain is involved through the time, and we are using two subsystems of the memory. One of them is called system one, is they're responsible for 95% of our decision-making, reasoning, and interaction with the world. This 95 is on autopilot and doesn't need that much reasoning in the brain to make any decision. But system two is rational thinking. It's much slower in the time scale, and also it's more cautious. We need to make reasoning more, maybe level of reasoning to make any action. And it's a more cautious way of decision making. But why we need memory systems is crucial for handling this long context, the temporal context that we already mentioned for the scenarios that is needed. It's essential for reasoning and planning in the complex scenario, especially with handling the edge cases, long tail scenarios, and enables continual adaptation to this new knowledge that every single day the data are collected from the roads. As I mentioned, if we collect every single day, do we need to retrain everything from scratch? Because adding this new knowledge, it's coming with other kind of, if we don't retrain or we don't train partially on the previously seen data, it comes with many more challenges like catastrophic forgetting that neural networks are suffering from. And then if we want to get closer to AGM, that one of the aspects is learning how to learn, we need this memory system to deal with those situations. The other very important gap that already exists with all this advancement in the field that we have with the large language models, with the word models, and so on, more larger and larger models are being trained with the more number of data points. But at the end of the day, for the embodied AI, which is autonomous driving, is one of those use cases. We need to deploy on some agent that it's living in the world and interacting with with its surrounding. And for this to be more sustainable, it needs to consume less energy. But the energy doesn't come only at the inference time, even at the training, like continual learning. If we need continually update the knowledge of these agents, we need also to make them efficient. But efficiency at the model level is one of the main challenging. If we decide to go to much smaller hardware usage, then there is a huge gap at the moment. Safety and reliability of the autonomous driving in general for both AV1 and AV2 are there, and they are still unresolved. There are several unresolved challenges there. This includes managing the unpredictable nature of open board deployment, handling the massive scale of the data from multiple sensors. At any given point of time, any of these sensors can fail, and then the system needs to be reliable and be trustworthy, that can decide if the rest of the sensors are enough, or at which case it can continue interacting with the world or just stop working. And ensuring utmost safety for all road users, making rapid, informed decision. Additionally, optimizing for efficiency is crucial to maintain high system performance. There is a lack of standardized and scenario databases for testing and verifying the AV systems. And the development cycle for autonomous driving in general is very slow, lengthy, and costly. And also deploying on the real world and testing for all cases is impossible because some of them are dangerous. And unclear and varying regulation across regions, going from Europe to Asia to US, there are many different rules that with different policymakers and regulators are coming. And it's really hard to handle all these different safety scenarios, although there is no agreement on what is called safety and what scenarios the system needs to be tested. So there is a new era of research that it's a still open question. The driving environment's complexity means number of scenarios for autonomous is virtually infinite. And studies suggest that providing an ADS is which is 20% safer than a human driver, requires over 11 billion miles, which is very huge and almost impossible to capture for very near future, and training our models and testing them. However, simply driving many miles, it's insufficient because a diverse range of scenario must be encountered to ensure safety. The key challenge lies in finding the right scenario that represent the ODD of the autonomous driving system, determining if enough scenarios have been identified to guarantee system safety, considering their probability of occurrence. And challenges include assessing the safety risk associated with each of these scenarios. And then after defining all these things, then we need to define what does it mean a good behavior or pass-fail criteria for autonomous driving in given scenario. Therefore, this safety is an open field, and also there is no consensus over that, and it needs more attention of the research community. Okay, I hope you enjoyed the tutorial and it was useful, giving you some just hint what has been done and where you can find those papers and what is a still open question, unresolved direction and challenges at the moment, and how we can tackle them. We are hiring at Wayve, and we are working on all aspects from simulation to word modeling, language for driving, efficient AI, and also the multiple memory systems, different architecture-based, very advanced and very novel. And if you are interested of any of these areas, we are hiring in London and Silicon Valley and Vancouver, our new science office. Please go and check our website and also come and meet our team at the booth.
Hi, Elahe. Not sure if you can see me, but this is Gijs, your colleague from TU Eindhoven. Thanks a lot for your great presentation. I have one question. If you look at the human brain, it has some modularity. And so you have parts of the brain that deal with very quick visual reflexes to stay safe. And you have parts of the brain that deal more with high-level reasoning. Now, in this era of end-to-end autonomous driving, do you think that there will be some modularity? Let's say a system of networks that can be trained end-to-end, but there is still modularity? Or do you think it will in the end be just one big transformer or whatever architecture?
Hi, guys. Thank you for the question. Yes, brain also has some subsystems, but none of these subsystems are trained individually and in isolation with the rest of the brain. That's some differences that we are seeing with the AV 1.0. But AV 2.0 could be subsystems of different modules that also it's called AV 1.5 even sometimes, that still we think, okay, perception and everything should be trained back to back and in an end-to-end kind of manner, but still we can have this subsystem. But AV 2.0, what we are hoping or what we believe is that there is emerging subnetworks that maybe is interacting with the world. Some of those subsystems, maybe lower layers, are responsible for perception, but we are not distinguished at what level this emerging of the perception should stop and the rest for the planning should start and so on.
Yeah, okay, clear. Thank you for your answer.
All right, let's thank again his great talk. And yeah, this is the end of the tutorial.